Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. In this video, we are going to discuss three sets of numbers. Okay. Number one, we call it irrational numbers. Number two, real numbers. And number three, complex numbers. Okay, now let's talk about the set of irrational numbers. Irrational. And the symbol we use for irrational number is Q prime. Q prime. Now, suppose that we have a right angle triangle like this. Okay, right angle triangle. Now, suppose that the length of this side is equal to 1 unit and the length of this side also equal to 1 unit. Now, according to Pythagoras Theorem, the length of hypotenuse from this point to this point is equal to square root 2. Now, when Pythagoras and his followers find this number for the first time, they were surprised because this number is not the number that they expect. Okay, because when they talk about numbers, they expect rational numbers. Rational numbers. As we discussed last time, we talked about rational numbers. Okay, what we mean by rational numbers is a number can be written as P over Q, where P and Q, both of them integers. Both of them integers. But square root 2 cannot be written as a ratio of two integers. And when we write down square root 2 in terms of decimal, we have square root 2 is equal to, we have 1 equal to 4 to 1. Then we have 356. Then we have 2, 3, ... and so on and so forth. Okay, as we mentioned last time when we talk about rational numbers, when we convert it into decimal like this, okay, there will be either two cases. Number one, either it is repeating and terminating, number one, and number two, whether it is terminate. Okay, in this case, if we look carefully at the decimal, okay, of square root 2, okay, the decimal on the right hand side here, it is non-repeating, okay, and it goes to infinity, or what we say, non-terminating. Okay, this is what we call the properties of irrational number. Okay, that is Q prime. That is, when we write down in terms of decimal, it is non-repeating and non-terminating. All right. Now, do we have any other irrational number? Yes, of course we have. Okay, the famous one is, for example, like pi, right? Pi, that is equal to, in terms of decimal, 3.14. We have 159, and then we have 265, and then also we have 35, and then ... Okay, the decimal continues to infinity without stop. And also, if we look at the decimal here carefully, okay, the decimal is non-repeating, okay, and is non-terminating, continuous forever. Okay, now some people say that pi is equal to 22/7. Now, this statement actually is not true because pi is not equal to 22/7. Okay, first of all, because pi is an irrational number, right? Okay, pi is in this set Q prime, but 22/7 is a rational number. This is an element of Q. This is irrational. This is rational. They are coming from two sets. All right. Of course, they are not the same. Approximation? Yes, I agree. Okay. Now, if we write down 22/7, okay, let's write down the value of 22/7 in terms of decimal. It is equal to actually 3.14 1, 4, 2. We have 8, 5, 7, and then we have bar above this 6 digit. Okay, that's mean 1, 4, 2, 8, 5, 7 repeat itself, okay, infinitely many times as we go along to infinity. Okay, this clearly, as we mentioned last time, when we have a repeated decimal like this, it is a rational number. So this is a rational number. On the other hand, pi itself is an irrational number. Okay, for pi, people also make many other what we call approximation of pi. Okay, other approximation of pi is we have people say is approximately approximated is equal to 355, for example, over 113. Okay, people also sometimes use this approximation of pi. This is about same value of pi, more or less, but not equal. Archimedes, still remember Archimedes? Yeah, one of the great mathematician lived around 250 BC. He says pi, okay, pi is in between 22 over 7. Okay, this approximation of pi given by Archimedes. Okay, greater than 22 over 7 and less than 223 over 71. If we ask Archimedes, what is the value of pi? He says it is in between 22 over 7 and 223 over 71. Greater than this number and less than that number. Okay, he cannot give the exact value of pi. He says in between these two numbers. So we already explained, okay, that square root 2 is an irrational number, right? Okay, we also have shown that pi is also an irrational number. Okay, what are the examples of irrational numbers? Yeah, it is square root of any prime numbers. For example, 3 is prime, right? 3 is prime. Square root of 3, yeah, it is also an irrational number. We have, for example, 11 is also a prime number. Therefore, square root of 11 is also in Q prime. That is also an irrational number. Now, beside prime, we also have what we call a non-perfect square. For example, 6. 6 is a non-perfect square. So, square root of 6 is also an irrational number. Now, for example, 10. Square root of 10. This is not a perfect square. Therefore, this is also in Q prime. How about 9? Square root of 9. Now, 9 is a perfect square. Square root of 9, this is equal to 3, right? Now, this is not an irrational number, okay? Because 3 is a rational number. So, that is other examples of what we call irrational numbers. Okay, now let's produce some what we call irrational number. For example, we have 1.01, 001, 001, 0001, 00001, and so on and so forth. Following this pattern, we'll also produce an irrational number. Now, let's give another one. For example, we have 2.035, and then we have 0035. We have 00035. Also, we'll produce another irrational number. Now, let's describe all the set that we have so far in the form of Venn diagram, putting them together. We have set n, that is natural number. Then the set of w, that is the set of whole numbers. Then we have another set that is bigger than that, that is set of integers. Okay, and we have even bigger set. Okay, that is the set of rational numbers. Okay, now the set that we have learned a few minutes ago, that we call the set of Q prime. That is a set of irrational numbers. Okay, this set and this set, they are disjoint. Okay, because they don't have any common element. Now, if this set and this set, we combine them together into one bigger set. Okay, thus we have the set of R. That is the set of real numbers. All right, so the set of real numbers is actually combination of the set of rational numbers and irrational numbers. Now, let's discuss another set of numbers we call complex numbers. Now, before we do that, let's recall square root of 4. This is equal to 2. Square root of 9 equal to 3. Now, how about square root of 1 is equal to 1, right? How about square root of negative 1? Now, here is the problem. Because from our previous sets, okay, we don't have square root of negative 1. Now, we have to create another set of numbers that we call complex numbers. Therefore, we define square root of negative 1 is equal to I. Or we say from here, this statement that is I square equal to negative 1. Therefore, what is square root of negative 4? This one is equal to, can break it down, square root 4 multiplied by square root of negative 1. Okay, this is equal to, this is 2, and this is I, right? Same like this. So this is equal to 2I. So any complex number, okay, can be written in the form A plus BI. Okay, where this is what we call real part. Okay, real part. And this is imaginary part. Okay, I hope you notice that, for example, 6. This is a whole number. This whole number is also a complex number because 6 can be written as 6 plus 0i. So this is the real part and this is the imaginary part. Therefore, if we write down in terms of Venn diagram, the relationship between real number and complex number, so real number, okay, we have real number inside and we have complex number outside. Okay, this means that real number is actually a proper subset of a complex number.